In this video, we will explore several more examples of improper integrals of the second type. So for an improper integral of the second type, it corresponds to a function having an infinite discontinuity. So in this case, let's say that as x approaches b from the left, the function f of x goes to plus or minus infinity. In that case, what we're going to have to do, and we'll just draw a picture to go with this. So we cannot evaluate with the fundamental theorem of calculus on this interval from a to b. The reason being, the function has some type of infinite discontinuity at b. So instead what we can do is say, how about we pick a value of t a little bit to the left of b, and then take the limit as we approach b from the left. Procedurally, the idea is the same as improper integrals of the first type. They can just be a bit more subtle to recognize. Once you've rewritten, you evaluate the definite integral and then take its limit. Let's evaluate a few examples. Let's evaluate the given integral. So minus 1 to 1 of 1 over the cube root of x. So let's just think about this graphically. So 1 over the cube root of x from minus 1 to 1. We have an infinite discontinuity at 0. The graph is roughly speaking going to look something like this. And note, because of this infinite discontinuity at 0, which happens in the middle of the interval, what we are going to have to do is break this up into two separate integrals. We're going to have to go from minus 1 to 0, 1 over the cube root of x, plus from 0 to 1 of 1 over the cube root of x. But no, we actually do not have to evaluate both of these intervals. We only need to evaluate one of the integrals. So let's make an observation that will help us. So for the function 1 over the cube root of x, this function is odd, which means it's symmetric about the origin. And recall from Calculus 2, or just from the graphical inspection, that if you're integrating an odd function, so minus 1 to 0 of the function, this will be equal to the opposite of the integral from 0 to 1 of 1 over cube root of x. And what that is telling us in the picture is that the area enclosed here in the first quadrant is equal to the same amount of area enclosed in the third quadrant, but because it's underneath the x-axis, you're going to need a negative sign. So if both of these integrals exist, i.e. they're finite numbers, then what that tells us is the value of this integral is going to end up being 0. But if we were to evaluate one of them and get back an answer that was infinite, then the integral itself, the improper integral, we would say diverges. So we're going to leave a little bit of space, and we'll go ahead and evaluate the integral from 0 to 1 of 1 over the cube root of x. And note, 1 over the cube root of x is really x to the minus 1/3. Now, because of this infinite discontinuity at 0, this is an improper integral of the second type. So instead of integrating from 0 to 1 all at once, what we are going to do is integrate from t to 1, which means we have to let t approach 0 from the right. So the limit as t approaches 0 from the right of t to 1 of x to the minus 1/3. And this is an extremely reasonable function for us to anti-differentiate. Minus 1/3 plus 1 is 2/3, and 1 over 2/3 is 3/2. So this would be 3/2 x to the 2/3 from 1 to t. So this will be the limit as t approaches 0 from the right. We plug in 1, so 3/2, minus sign, plug in t. Because the power of t is positive, as t approaches 0 from the right, that term is going to go to 0. And the value of this limit is 3/2. And we now are able to determine the value of the original integral. So coming back to our observation, we've evaluated the integral from 0 to 1 and found that it is 3/2. Which means if we go from -1 to 0, the value is going to be -3/2. So for our improper integral, we have -3/2 plus 3/2, and the value of this improper integral is 0. Let's now evaluate the integral from 1 to e of 1 over x ln of x. Recalling that ln of 1 is 0 shows us that we are going to have an improper integral of the second type. There's an infinite discontinuity at x equals 1. So there's an infinite discontinuity. So this is an improper integral of the second type. So we rewrite it as a limit. So this will be the limit as t approaches 1 from the right-hand side, the integral from t to e, 1 over x ln of x dx. So we now evaluate the integral and then take its limits. So in terms of the integral, we see that we have this nice form, an ln of x, and then its derivative, 1 over x. So we're going to use a u substitution. So we'll let u be equal to ln of x, so that du is 1 over x dx. So the 1 over x dx is our du, and the ln of x in the denominator is our u. So rewriting the integrand, we're going to have the limit as t approaches 1 from the right, and we'll be integrating 1 over u. But we do need to change our limits of integration. So for the lower limit of integration, when x is t, looking at our substitution, u will be the ln of t. For the upper limit of integration, when x is equal to e, u will be the ln of e, and the natural log of e is the number 1. So we now anti-differentiate. The antiderivative of 1 over u is the natural log of the absolute value of u. And by the fundamental theorem of calculus, we plug in from ln of t to 1. So this will be the limit as t approaches 1 from the right of the natural log of 1 minus the natural log of the natural log of t. So the natural log of 1 is equal to 0. So that first term simply vanishes. Now if we think about taking the limit as t approaches 1 from the right. So as t approaches 1 from the right, the natural log of t term is going to be approaching 0 from the right. And if we're plugging into the natural log really small positive numbers, what that tells us is that the natural log of the natural log of t is going to be going to minus infinity. So in terms of our limit, it's going to be approaching minus a minus or a positive infinity. So this improper integral of the first type, we would say in this case diverges. It does not approach a finite constant.